Here we are. What do you need to know about the normal distribution? A, it's a really cool looking curve. It's named after this guy, Gauss, because that's also called the Gaussian distribution. It is a theoretical curve. It is perfect. The mean is equal to the median is equal to the mode. More important than that, when you move out different distances on the normal curve, distances in standard deviation units, you will capture a very precise, reliable, 100% every time kind of percentage of the data. So if you move one standard deviation from the mean to the normal, from the mean to some other point on the normal curve, you move one standard deviation above the mean. Between the mean and that new value, one standard deviation away, you will capture 34.13% of the data all the time, every time. Move in the other direction, you capture 34.13% as well. If you move a second standard deviation, so you move two standard deviations from the mean plus 1 plus 2, there you're going to capture about 47.75% of the data. If you go in the reverse direction, mean minus 1 minus 2 standard deviations, again it's still 47.75% of the data. Together, between one standard deviation above and one standard deviation below, you're going to capture about 68% of the data, 68.26%. If you move two standard deviations above and below, you'll capture about 95.5% of the data. Now, people don't like to use those kind of weird numbers, and so people like to talk about 95% of the data. So what captures 95% of the data in a normal curve? Moving exactly 1.96 standard deviation units above and 1.96 standard deviation units below the mean. Last thing about the standard curve is z-scores. Z-scores simply tell you where you are on a normal curve with respect to the mean measured in standard deviation units. So if you have a z-score of 1, that means you're 1 standard deviation above the mean. If you have a z-score of 0, it's equal to the mean. If you have a z-score of minus 2, you are 2 standard deviations below the mean. And you can do all those intermediate calculations as well. That's the normal curve. It's a theoretical curve. It's used to describe the distribution of data. It's used in the creation of various mathematical principles. So now, we're not going to talk about the whole derivation of the concept of the standard error of the mean. We'll talk about the simple way that you calculate the standard error of the mean. If you have a sample, you simply take the standard deviation of the sample and divide it by the square root of n. That is, by definition, an estimate of the standard error of the mean. So if you had a sample and you needed to get the standard deviation, you'd first calculate the variance, which is the sum of the squared deviations from the mean divided by n minus 1, because it's a sample. That's the variance. Take the square root of that variance value, and you have the standard deviation. Divide that value by the square root of the sample size, and you have the standard error of the mean. Understand that that's only an estimate of the standard error of the mean. The standard error of the mean is another cool theoretical concept that comes from this thing called the distribution of sample means, which we won't get into in this particular video. What do you do with the standard error of the mean? There's only one legal thing you're supposed to do with the standard error of the mean, and that is to use it to calculate a confidence interval. A confidence interval is nothing more than a range of values centered around the sample mean that tells you that you are X% likely, this confident, to capture the true population mean in that range. So if I have a bunch of data in a population, 130 values, let's say, and the sample mean is 100. That's my best single point guess for the population mean. But if I want to get a confidence interval, I'll calculate the variance of that sample. I'll calculate the standard deviation of that sample, divide that standard deviation value by the square root of the number of subjects, square root of n, and that will be my estimate of the standard error of the mean. If I move 1.96 standard error units away from my mean, above and below, I have the 95% confidence interval. I am 95% confident that the population mean from which I drew my sample is in that range of values. That calculation, confidence interval equal 95% confidence interval equals 1.96 times the standard error of the mean, works every time, all the time, as long as the sample size is big. Big meaning 120 to 130. If the sample size is smaller, then it is underestimating the value of the confidence interval and you're overstating your actual confidence in the data. If the sample size is small, you can't use the normal curve. You have to go to what are called t-distributions. And so basically, if the sample size is 50, with t-distribution of 50, I have, say you have a sample of 50 values. You have 49 degrees of freedom, because it's n minus 1. We'll get into that later. But basically, you have to look at a value that's kind of like the 1.96, but it's going to be more like 2.5 or 2.1 or something like 2.1 for 50 degrees of freedom. So your confidence interval will be a little bit wider when you multiply the standard error of the mean by the t value, which is going to be higher than 1.96. Simply put, for any and all samples, the confidence interval is essentially that point, the 95% confidence interval, is that point that's 95% likely that your true population mean will fall in that range, and it's centered around the sample mean, and is based upon primarily two things. One, your calculation of the standard error of the mean for the sample that you have, and you do that by calculating variance, standard deviation, and then standard error. One of the factors is standard error, as I said before. The other is the distribution that you're looking at. If it's a huge sample, more than 125, it's a normal curve. You multiply by 1.96. If it's not a huge sample, if it's 50, if it's 20, if it's 10, you multiply by an appropriate t-value that will be higher than 1.96 and getting bigger and bigger as you go from 125 values to 100 values to 50 values to 30 values to 10 values to 5 values. But all of those calculations do the same thing. They give you the range of values centered around your sample mean for which you are 95% confident that your true population mean is in that window. That's what we're trying to talk about when we talk about the normal curve, to open things. Then we talk about z-scores and the distribution of data in the normal curve. Then we talk about confidence intervals. We did not in this discussion even talk about the distribution of sample means. We'll talk about that in class, and it's in the other videos. This is the most out of the weeds we can be on this discussion. I'll see you on Thursday.